In this video, I will discuss a process that an ideal gas system can undergo. And what I've done here, I have summarized the theory for you. Now, I do want to use the PV diagram to show you what the process is on the PV diagram. So to remind you, on the vertical axis, I have the pressure. On the horizontal axis, I have the volume. I can mark a state of an ideal gas system with a dot because a dot represents a specific pressure and volume. And when you know the pressure and the volume and how many moles you have, you can find the temperature. So you have these variables that describe your system. And if you have two dots, one dot here and one dot there, this means that you have two different states of your system. So here your system has one pressure, one volume. Here your system has a different volume and a different pressure. It's still the same system. We're still talking about the same atoms, the same ideal gas, but it has a different, it's in a different state. By a process, I mean the way with which your system goes. Now, this is supposed to be a smooth line. Let's see if I can do a little bit better. By process, I mean the way with which the system, let's see, something like this. Okay, let me try one more time. I don't want to do a straight line because I want to indicate that I have an isotherm. So this is the process. Okay, here is state 2, here is state 1. This curved line represents a process. This is a process. The process with which the ideal gas goes from this pressure and volume to that pressure and volume. Now, for processes, we have a number of processes for the ideal gas. When you hear the term isochoric, that means that the change in the volume of the ideal gas is zero, or in other words, the volume of the ideal gas stays constant. The term isochoric has a Greek origin. Iso for equal, and choric is about volume. So an isochoric process means that the volume of the gas stays the same, and because the volume of the gas stays the same, the work that the ideal gas does is zero. Okay, for a gas to do some work, it has to have some displacement. And when we're dealing with gases, a displacement really means a change in volume. If the change in volume is zero, there is no work done. Another kind of process that an ideal gas that you can use with an ideal gas is an adiabatic process, which means that Q is zero. And it has been shown that the pressure times the volume times the gamma constant is this expression is a constant during an adiabatic process. In an isobaric process, the pressure stays constant. And if you have a PV diagram, an isobaric constant, since an isobaric process where the pressure stays constant, to keep the pressure constant, you have to be moving on a horizontal line, either left or right. But that's what indicates an isobaric process, constant pressure. And I forgot to mention, for an isochoric process where the volume is constant, this would be indicated on a PV graph with a vertical line, since the volume stays constant. And the last one, I forgot. So for an isobaric process, the work done by the gas can be calculated as the pressure times the change in the volume. And also Q, heat, can be calculated as the number of moles times the specific heat under constant pressure times the change in the temperature. We have one more. An isothermal process is one where the temperature stays constant or the change in temperature is zero. And this is what an isothermal process looks like. The temperature stays constant. It is a curved line. It is complicated to find the area under curved lines, and I have given you here the expression for an isothermal process. nRT, the natural log of the final volume over the initial volume. And because this process has the same temperature, if you go here and you plug in delta T of 0, you will find that the change in the thermal energy of the ideal gas is 0. This is true for isothermal processes. Now, and there is one more thing that I want to mention that is valid all the time for all of these, not just one. Okay, everything that I mentioned here is specific to isochoric processes and so on. That's why I have separated into different segments. Now, what I did here, I wrote the energy conservation principle. And on the next step, I said the change in the energy of the system is the change of rest energy, the change of kinetic, the change of potential, plus the change in internal. Now, for rest, kinetic, and potential, we have those changes are all 0. So the only thing that I have is the change in the internal energy of the system. And for an ideal gas, where I'm assuming there are no chemical reactions going on, the internal is all thermal. So from here, I obtain this expression: the change in the thermal energy is equal to the work done plus Q. This is how you can apply energy conservation for an ideal gas process. You don't have to start, you don't have to write this and then the next step and so on. Just when you work with ideal gas processes, just go ahead directly and use this. Just remember that it comes from the energy conservation. Now, I do want to mention one last thing. Here you see W. Here you see W, W, W. All of these are work. These W's are about work, but you have to be careful what work they are talking about. So this is in energy conservation, in this physics principle, the left side is about the system, the right side is about the interactions. This is the thermal energy transferred from the surroundings to the system, from the surroundings to the gas. This is the work the surroundings do on the system. For us, the system is the ideal gas. Okay. Now here's where you have to be careful. This work and all of these W's here, this is the work that the system does on the surroundings. And the same thing is true for this work and also for this work. So you have to remember this. Now, what's the difference? This is the work that the system does on the surroundings. This is the work the surroundings do on the system. So I'm just moving the two words around. But it is important because those two are not the same. They are not equal. In fact, they are exactly opposite. So when you use these expressions to find W, to find the work done by the system on the surroundings, before you plug it into the energy conservation principle, add one more minus. So you do this calculation, you find the work that the system does, then add whatever number you get, put a minus in front to before you use it for in the energy conservation expression. Okay. Now, This is the theory that you need, and I try to summarize everything on this single whiteboard. It's quite a lot of expressions. It will I find it very helpful for me when I work with an ideal gas that goes through several processes and there are several states. I do find it very helpful, extremely helpful, to have all of this on a piece of paper or somewhere written where I can easily find it before I start working. Because having to find every single expression from here on a different place, on a different page, or on a different slide, whatever, it does take time, and it just makes things much more difficult. So I strongly recommend that you have that all of these, that you summarize, you write it down on a piece of paper, or use my equations handout, the PDF, and use it as you need to make things a little bit easier for you.